Okay, so let's have a look at the variety of types of equilibria that you can sustain under repetition in a game, an infinitely repeated game. So we'll have a look back at a repeated prisoner's dilemma, but now a more complicated equilibrium that we can also get out as part of the structure of repeated games. So in particular, let's look at a prisoner's dilemma where when we cooperate, we each get a payoff of 3. But when one player defects and the other one cooperates, they get a payoff of 10. So an enormous incentive to deviate when the other person cooperates. And then a payoff of 1-1 from the defection equilibrium. So here again, we have the normal prisoner's dilemma structure in the sense that defect is a strictly dominant strategy. And the interesting aspect of this game, though, is that if you notice here, the total payoffs from cooperation, if both players cooperate, the total payoffs we get are 6. Whereas if one cooperates and the other defects, we get a payoff of 10. So the total payoffs are better in situations where one player cooperates and the other player defects. And the worst situation here is they both defect. Okay, so what's the difficulty with this game? Well, the difficulty with this game is that in terms of maximizing overall payoffs, we'd like to have one player cooperate and the other defect. But who wants to be the cooperator? Neither would like to be the cooperator because they're going to get a low payoff while the other gets a high payoff. But in repetition, we can have a situation now where we can end up having one player cooperate, the other defect, and then reverse in even and odd periods. So for instance, if we think of this as like a commons game where there's only room for one player to be, say, fishing at a time, then what we'll do is we'll have in even periods, the row player will defect and the column player will cooperate, and then in odd periods we'll reverse that. And then how do we sustain this? We sustain this by going back to the one-shot Nash equilibrium and playing both defect forever after if anybody ever deviates from what their prescribed strategy is. Okay, so let's try and figure out when this would be sustained as a strategy, as an equilibrium in the infinitely repeated game, as a subgame perfect equilibrium in the infinitely repeated game. So if I follow strategies, let's suppose that I'm supposed to defect in the first period, so cooperate in the first period, and the other player is supposed to defect, so I get a 0 in the first period. Second period, I get to be the defector, the other person's supposed to cooperate, I get 10. Then we reverse, I go back to 0, then I go to 10, and so forth, right? So here in odd periods, I get 0, and even periods, I get 10. And so we can look at that payoff. If I deviated, well, I'm not going to want to deviate in a period where I'm getting the optimal payoff of 10. I'm going to want to deviate in a period where I'm supposed to be playing the cooperate and the other person gets the defect. And so the benefit here is that I'll get 1 by instead defecting myself as well. But then forever after, we're just going to stop cooperating and defect forever after. So then we get 1 forever after, right? So what we can do is we can look at what the payoffs of this are. So the payoff of this series is just going to be 1 over 1 minus beta I, where that's my discount factor, right? So I get that payoff from this series if I deviate, and then we defect forever. Instead, if I follow the prescribed equilibrium strategies, what am I getting? Well, if you sum this series, it's basically a series where I'm getting 10 in every other period, starting in period 2. So that's going to look like beta I times 10 over 1 minus beta I squared. So it's as if I'm hitting it with a discount factor of beta I squared, right? So a beta I times the whole sequence plus my discount factor looks like it's every second period that I'm getting payoffs. So it looks like beta I squared as my discount factor. Okay, so in order to check that that's an equilibrium, then what do we do? If I follow strategies, I'm getting this payoff, deviate getting this payoff. So we need to check when is it that I would rather follow the prescribed strategies than deviate. I need to have the payoff of 10 times beta I over 1 minus beta I squared be at least as high as 1 over 1 minus beta I. You can just solve through for that, and basically that's requiring, bring this up to the numerator over here, divide through. You want 10 beta I greater than or equal to 1 plus beta I, and that's true if beta I is greater than or equal to 1/9. So here, very low discount factor is enough to make this work in this game, basically because we have an enormous gain of playing the prescribed strategies. We get this payoff of 10 every other period versus getting 1 every period, and 10 every other period is better than 1 every period as long as my discount factor is bigger than 1/9. Okay. So what have we seen? That's a more elaborate equilibrium, but what happens with repetition is that there's a lot more that we can sustain based on threats of reverting to play that's going to give us lower payoffs. And the fact that these things are open-ended then allows for a whole set of equilibria to emerge. So the good news is that players can possibly get higher payoffs than they could in a situation where they're not able to take advantage of this. The bad news is that there's an enormous number of equilibria, and it's not clear what might happen or how players coordinate on these things. So just sort of to summarize a little bit, in terms of repeated games, if we've got sort of a unique Nash in a one-shot game, then that's going to be unique in a finitely repeated setting. So one really needs a setting where there's some chance of continuing on beyond any particular point. So with either infinite or at least indefinite, so I'm not sure when the end of the game is going to be. There's no period where I know that we won't play beyond that period. Then the threat of reversion to one-shot Nash equilibrium can support strategies with higher payoffs. And actually, there's a whole set of other types of threats that can sustain different forms of equilibrium, and the set of equilibria explodes. But basically, the intuition is that players have to anticipate what's going to happen in the future. They need to care about the future, and they realize now that their actions in one period can affect the future evolution of the game, and that changes their incentives dramatically compared to one-shot settings. So repetition is a dramatically different concept than a one-shot or even just a fixed set of repetitions of a game. Now, one application of this, and I think that this is sort of an important insight and one of the more basic insights that came out of game theory over the past few decades, is that this allows players to really change the way in which they behave. And when we think about concepts that are related to this, things like social norms or culture or other kinds of things, the fact that we have repeated interaction between individuals allows for teamwork, it allows for cooperation, it allows us to share risk, it allows us to exchange favors. There's all kinds of interactions where we don't rely on courts or some sort of external enforcement, but we rely on the fact that if we don't behave ourselves today, there's going to be consequences in the future in terms of the way that other people are going to retaliate against us, and that makes behavior of individuals much easier to sustain than in a situation where there's some sort of finite repetition to the setting. So this has been a very exciting and interesting area of game theory, and one that has very far-reaching applications and lots to say about how people behave in all sorts of applications, from very simple ones in developing countries where we're looking at whether or not people are able to share crops with other people that might be experiencing crop failures, to the way that companies behave in a complicated marketplace.